time. I am a machine learning research engineer, so I currently do research in low resource NLP and privacy preserving ML. So I guess I can share my screen now. So we can get started. Okay. I hope everyone can see my screen. So give me some few minutes, guys. I'm just going to share my screen. Can everyone see my screen, please? Please kindly confirm if you can see my screen. Okay, awesome. Good. Yeah. Okay, so today we'll be talking about putting up the attention mechanism. And I've briefly talked about myself. So I currently do research in NLP and privacy, so specifically in low resource NLP and privacy preserving machine learning. So we'll be talking about the coding attention mechanism. So before we get started, a refresher on what we did previously. So if you were in attendance in my last section, I talked about how to design your data pipeline to get it ready for LLM training. So this section continues from where I left off in my last section. So you probably might notice that this continues from where we stopped in the last section that I held. So for coding attention mechanism, I designed this talk to be in such a way that we are going to break down the components. We are going to look into the attention mechanism in a more mechanistic way. So we are not just going to do live coding. So the goal is for us to be able to understand each and every component that is in the attention mechanism. So I designed this section to be able to help us to understand each segment that we have in the attention mechanism. So we are going to be doing a bit more of breaking things down and fixing it. So once we've been able to get the overview, at some point I'm going to switch to the code for us to see how exactly this ties in with what I'm going to explain or what I'm going to talk about today. So we are going to start off by refreshing our memory on how to design your LLM data pipeline. So if you were in my last section, we talked about the steps or the techniques that you need to ensure that you have in place for you to get the data that you want to use in training your LLM ready. So we moved from getting the text data, performing your tokenization. Then once you've performed your tokenization, you have to get your token ID, which involves you creating a vocab for you to be able to get this token ID. So once you've gotten your token ID, the next step is for you to create a token embedding. Once you've created your token embedding, the next step is for you to add some form of position information to the token embedding that you already have. So you are adding the position embedding with the token embedding to finally give you your input embedding, which is then what you're going to feed your decoder. So the bulk of my talk today is going to focus more on this, since we've already covered this segment that you are seeing here. So we are going to be focused on the second step in stage one of training your LLM, which is the attention mechanism. So most of us already know, but if you don't know, we have different types of attention mechanism. So the way I structured this slide or this section is that we are going to start off by looking at a very simple implementation of self-attention. In fact, the attention mechanism that doesn't involve any trainable weight. So once we've been able to contextualize what exactly this simple attention mechanism is all about and what it looks like, it's then going to make more sense when we try to enhance what we are doing here to incorporate trainable weights to the attention mechanism that we've discussed in step one. So we have these 4 different variants of attention mechanism that we are going to look into this section, but we are going to start off with the simplified self-attention before moving to self-attention. Then the third one is going to be the causal attention mechanism, which is sort of where you start masking future tokens from your model. So your model is only limited to the current token and the previous token that it has seen. The multi-head attention is where you start multiple self-attention. So these 4 different types of attention mechanism is what we are hopefully going to be able to cover today. So, well, before we get into the coding of the attention mechanism and what attention is all about, let's start off by what exactly led us to this attention mechanism in the first place. Which problem were researchers trying to solve before they discovered this guy called attention? So we are going to look into the problem that is prevalent with modeling long sequence. So before the era of LLM or your transformer architecture, there is this problem that comes with when you are working with long input sequence, or when you're working with a very long sequence. This problem that led to the introduction or the discovery of this attention mechanism is what we're hopefully going to start off with to enable us to see the steps that we are taking before this attention guy was discovered. So imagine that you have this sentence, this German sentence, and the goal is for you to translate this sentence that you are seeing here to English. Now, if you look at the first German tokens that we have up here, you are going to notice that if we try to translate each of these words word for word from your input text to your target text, you are going to notice that the translation is not going to make much sense. So the reason is because of the nuances or the grammatical structures that exist between your source and your target language. So because these 2 languages are not they are not exactly the same, so we can't just translate word for word. So if we are to translate this German text that we have here, it's going to give us this, can you help this sentence to translate, which doesn't really make sense. But what this sentence is just trying to, what this German sentence translates to in English is, can you help me to translate this sentence? So now we could see that it's not exactly possible for us to just translate this German sentence that we have here word to word without considering the grammatical structure that is important for us to consider when we are trying to translate from our source to our target language. So, but before the era of LLM, what was invoked then was that there is this deep learning architecture that is being used. So most of us here must have heard of RNN, which has the encoder and the decoder side. So the image that you're seeing here is the encoder side. So what exactly this encoder guy does is takes in this text that you are trying to translate. Remember, we are trying to translate from our source language to the target. So our source here is a German language, and it's the target that we are aiming for is the English translation of the German text. So what the encoder then does is that the encoder is going to take in this, your input sequence that you have, this cans domain. It's going to try to process the entire thing that you have here, and then pass off this pass off this now to the decoder for the translation to take place. And with RNN, there is this concept of hidden state. So when you pass the first input token, it goes in here. The hidden state that you have for the first input token is then stored. This hidden state is then propagated towards the last token that you have in the source text. So the last token that you have in the source text, which is this, is also going to produce its own hidden state. Now you could see that this last hidden state that we have in this encoder side is what we refer to as the memory cell. So this memory cell that you have here, it's going to try to encapsulate or take in all the previous information that was passed from the first hidden state up until where we have the memory cell. So this then is what's going to be fed to the decoder. So from here, the translation then starts taking place. So now let's look at the issue that most researchers encountered when they tried to translate a very long sequence using RNN. So the main problem with using RNN to perform translation is that it doesn't really do much when you are trying to translate a very long sequence. Your RNN is going to be very much suitable and very good if you are trying to translate a sentence that is not so much. Now imagine that you are trying to translate maybe a Harry Potter book. You are trying to translate it from, say, maybe English to German, for example. When you are using your RNN to do something like this, the result is going to be subpar. It's not going to be 100% perfect or good because of the problem or the challenges that you are going to encounter when you are trying to work with a long sequence. So with this problem in mind, so this is one of the issues that led to the discovery of this attention mechanism guide that we are about to discuss today. So if you could just flash your mind back to this last picture that we have here. So now imagine that every hidden state that you have, it's going to be, so the first hidden state is going to be propagated until you get to your memory cell. So this memory cell is now going to try to hold every information that it has encountered so far. So imagine that you are trying to translate a very long sequence. Case in point, the Harry Potter book now. Every information that it has seen, it's going to try to store all of it here. And what then happens with translating long sequences is that it will get to a point where it will get to its forgetful state. So forgetful state now becomes a very big issue because your encoder or the memory cell now will try as much as possible to accommodate every information that it has seen before. And when you are passing this, your memory cell, you are giving it to the hidden state of your decoder. The issue now is that this your decoder only have access to this guy. It doesn't have access to every hidden state that has gone past the memory cell. So that's the reason why when you are trying to use your RNN for your long sequence translation, it's going to get to a point where it starts forgetting what it has remembered, which is going to lead to a subpar performance. So because of this problem, the researchers that were working in NLP then tried to resolve this. So in particular, the Cardinal attention mechanism was then proposed for RNN in 2014. So what this exactly helps? So the new idea that is introduced is that with this Cardinal attention mechanism, these guys sort of figured out a way to make it possible for the hidden states that you have in your decoder to somehow have access to every input token that has gone past the encoder state. So this picture then tries to sum up what I've just pointed out now. So with this in mind, you still have your encoder side of things, and you also have your decoder side of things. But then what's been introduced is that there is now a way for us to be able to access the input tokens that the encoder has seen without having to struggle much. Not until 2017, this Cardinal attention mechanism was still very much in vogue. But later on, just 3 years apart, researchers discovered that you don't really need RNN architecture if you're trying to work on NLP problem. So, which then led to the proposal or the introduction of the transformer architecture. So this transformer architecture was then released in the year 2017. So what the transformer architecture then established is that you don't actually need RNN for you to be able to build a deep neural net for NLP. So with the incorporation of the self-attention mechanism that was introduced by Badnow, this transformer architecture happens to still be one of the most popular discoveries that the AI industry has seen. So since you can imagine, so since 2017, this transformer architecture is still very much popular and still very much in vogue, because with the LLMs that you probably interacted with, there is always this transformer architecture thing that is happening behind the scene that is powering all the magics that all the capabilities that your LLM could do. So now let's look at this attention guy. So with self-attention, like I mentioned before, is the key or is the main guy that powers this transformer architecture, which was introduced in the year 2017. So from here henceforth, you might want to pay a little bit more attention, because now we are getting to the core topic that we want to talk about, which is self-attention, or one of the variants of attention. This part that you are seeing here, we've talked about it before. So this first stage is for the data pipeline. Then the second stage is where I want to focus my energy on for now. This third stage that you are seeing here is what then happens after you are done with the second stage. So the self-attention refers to the ability of this mechanism to be able to compute the weight of each and every individual element that you have in your input sequence, including itself. So you understand better when you see. So now, imagine that you have this as an example. This is your input text, your journey starts, blah 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 step. So what then happens is that you are going to have you're going to have this text tokenized and pre-processed. So that's the first stage. Once you've gone past the first stage now, which is then going to lead you to creating the input embedding. So what then is going to happen is that we are going to now create have a input vector. So each token that you have in the text is going to have its own input vector. So this vector belongs to the first token that you have. This belongs to the second one. This belongs to the third, and this belongs to the fourth one. So the goal here, or this example, in this example, we are trying to compute the context vector of the second token that we have here. So for us to be able to compute this context vector for the second token that we have here, it then means that we need to calculate the attention weight of this second token that we have here with respect to each and every individual token that we have in this input sequence. So simply put, what I'm trying to say is that you have this guy called Johnny, which is the second token that you have here. If you would like to compute the context vector for this second token, you have to first of all compute the attention weight of this guy with respect to your. So we want to know how important is this first token that we have here with respect to Johnny. How important is Johnny with respect to itself? How important is this Johnny with respect to stars like that, like that? So once you've been able to compute this, that's what's going to give you your attention weight. So this guy you are seeing here then becomes the attention weight of the first input token with respect to Johnny. This becomes the attention weight of the second input token, which is the guy we are interested in, the attention weight of Johnny with respect to itself. This then becomes the attention weight of your third input token with respect to Johnny, etc. So once you've been able to compute the attention weight, is this that attention weight now that you can then use to get the context vector for the second token that we have here. So talking of context vector, what exactly is context vector? So what this context vector guy helps us with is, it's just something that helps us to understand the relevance of each word that we have in our input sequence with respect to every token that you have in that sequence. So just like in the last slide, I showed us that it's possible for us to know the importance of the first token, which is your, with respect to Johnny. So when you compute this importance, or when you compute this, the attention weight of each and every individual token that you have in your input sequence with respect to a particular token of interest, or the current token that it's been that you are currently interested in working with. This is going to then give you the context vector for that specific token. So this context vector is simply what helps us to understand the importance of words that we have in our sequence with respect to itself, and as well as each and every other sequence that you have in your input sequence. So to simplify things, let's because I believe that you understand more when you see. So we are going to start off by implementing a simplified version of self-attention mechanism to actually understand what all these things is all about. So what you are seeing here is, just assume that this Johnny, this is the vector for Johnny, for your, this is the vector for Johnny, this is the vector for the input vector for start, for etc. So what you are seeing here is your input sequence. Your Johnny starts with one step. So that means that we have x1 to x6. And for each of these inputs word that we have here, or token that we have here, they all have their corresponding vector. So this vector you are seeing here belongs to this guy. This one belongs to Johnny, like that, like that. And for brevity's sake, or for us to be able to understand without having to rack our brain so much, I made the embedding to be in a size of 3. So that doesn't mean that you can't have more than three values that you are going to use to represent a token. So this is just for us to have a very good understanding of what's happening without having to do high-level calculation, or people easily getting lost before we even get to the main points that we want to hit. So this guy that you are seeing here just has an embedding of size 3. It's also possible for it to have an embedding of size 1 million. So this is just for us to be able to contextualize things very easily. Okay. So the first step is for us to be able to compute the attention scores. Now remember that this is our input. Your journey starts blah, blah, blah step. The first stage is for us to be able to compute this attention score that we have here. So in order for us to keep things very structured and simple so that everyone will follow what exactly is happening, I try to make each value that we have here to just be in a 1 decimal place. So this 0.4, 0.1, 0.8 you are seeing here corresponds to what you are seeing here. So 0.4, 0.1, 0.8. So for the second token, you have 0.5, 0.8, and 0.7, 0.6, sorry, which is what you are seeing here. So these values, these numbers that you are seeing here corresponds to what each input vector that we have. It corresponds to whatever token that you're looking at a particular point in time. So for our first input token, we have this. For our second input token, we have this, like that. So the first step is for us to compute the attention scores. And for us to, and remember the overall goal is for us to be able to get the context vector for this guy called Johnny. So since this guy called Johnny, which is the second input token, is still what we are very much interested in. So we are going to refer to this guy as a embedding query token, which is exactly what you are seeing here. So given that the first step is for us to compute the attention between each and every individual token that you have here with respect to this X2, which is a embedded query token. The step for us to proceed is for us to compute this attention score. Once we've been able to compute this attention score that we have here, we can then be able to deduce or get the context vector of the second input token that we have here. So this just points to the attention score between X1 and our query, which is X2. That's the relationship between this guy and this guy that's going to give you this attention score that you have here. So for this guy is the relationship between this your embedded query token with itself, because they are exactly the same. For the third one, you are also going to try to compute the attention score between the third input, which is this guy, and the query token that we are interested in, which is going to give you this attention score that we have here. So that's exactly what's going on here. Now, once you've gotten this attention score, you can then use this attention score to compute the context vector. Now, remember, what this image is trying to tell us is we are trying to compute the context vector of the second input token that we have here, which is the reason why we made the input vector of second input token to be our query token here. So for us to be able to compute this attention score, we need to perform dot product. So this is an overview of how to do it. It's not exactly something that is all overly complicated. So when you now remember that since the guy that we are interested in is our embedded query token, is the second guy. So that's why here I'm indexing this tensor so I can pick the second guy that we have here. When you index your inputs with 1, it points back to Johnny. So we want to be able to compute the attention score. And for us to be able to do this, we simply have to do dot product. We have to get the dot product. So this code is showing us that the attention scores of the first input token with respect to this guy called Johnny is this, like that, like that. So the second input token, which is Johnny with respect to itself, as the attention score for the second one, the third one, and like that, like that. So this is the result that we are going to get when you perform your dot product. So we could as well refer to this result that you are seeing here as our computed attention scores, which we got by simply performing dot products. So now if you're wondering, okay, what exactly is dot product? So dot product is a way for us to, let's start by the mathematical concept. So when you perform dot product, it's just a concise way of us taking two vectors, and when you multiply the elements wise, it's going to give you a scalar, which is a single value. So this scalar, or this result that this dot product gives you, is what helps us to weigh the importance of that particular the importance of the relationship between the first vector and the second vector that you multiply. So it sort of tells us how similar so for example, if you perform dot products for between the first token that you have and the second token, and you arrive at a specific value. So this value is what tells you how similar your is to Johnny. So if you're doing the same, you get the attention score for Johnny versus the third input token that you have in your sequence. It's then going to tell you the similarity between the Johnny guy, which happens to be a second input token, with the third input token that you have in that sequence. So in other words, this dot product thing here, it helps us to quantify similarity. It helps us to know how exactly is these two guys that are multiplying, how similar is these two guys. So when you perform your dot product, you'll be able to have this value that helps you to quantify how similar things are. So in other words, the higher the value of your dot product, the more important that word is to whatever your query token is. So in our case, since we've decided to make the second input token our query token, so it means that once you've performed your dot product, so if you look at what you have here, you are going to notice that you have 0.9, 1 point. So these values is simply trying to tell you how important is each and every token that you have in your input sequence to the word Johnny. So whatever the highest word is, or whatever the highest value is, so this points you to, this enables you to be able to quantify how exactly is, for example, this last input token to Johnny. So the value that we have here is 1.0. The value that we have here is 0. So this is simply what helps you to quantify how similar this guy is to this, how similar is this to itself, how similar is Johnny to start, etc. So for us to be able to get these values, we have to perform dot product. So now, after you've gotten your attention score, the next thing is for us to be able to get our attention weight. And for us to get the attention weight, by the way, the values that you are seeing here, this 0.9, 1.4, 1.4 to 1.0, it's exactly the same value that we got here when we perform this dot product. So it's also nice to point out of this so that when you are going through the slide, you'll be able to understand what the pictures and even the code is trying to do. So this 0.9 you are seeing here is because the dot product that we got also has 0.9 something. But remember that I'm always going to limit it to one decimal place so that we don't can preserve space and not have a lot of words, a lot of numbers. So this is also going to help us to understand better what exactly is going on. Once you've gotten your attention score, the next thing that you need to do is that you need to normalize. So when you normalize this attention score, it's going to give you the attention weight. So the goal is that when you sum this, when you add all these values together, it must sum up to 1. So that's the essence of us normalizing, because when you don't normalize, it becomes a bit more hard for us to say that, oh, that this particular token has more similarity to Johnny. It's not going to be as as easy as it's going to be when you are working with when you are working with an already normalized attention score, which exactly is what your attention weight is. So when you normalize your attention score, you get your attention weight. So here I showed how to perform the normalization. So what you then have to do after you've completed your dot product and you've stored it in this variable called attention scores too. The next thing is for you to get your attention weight. And for us to get our attention weight, we have to normalize the attention score that we've gotten. So by normalization, you simply have to divide by the sum. So you have to take the sum and you have to take the attention score that you've gotten and you divide it by the sum. So when you do this, it is going to give you your normalized attention, so which we can also refer to as our attention weight. Now, when you sum these values that you have here, it's going to give you 1. Okay, so it's more common to see people using softmax function to perform normalization instead of just using just performing dividing by the sum that we have. So we simply, by the way, what this is once you've gotten your attention score, just sum all the values that you have there. So take, for example, this is our attention score. You have to add all these numbers together. When you add all these numbers together, it's going to give you a value. So that way, what you are then going to do is that you are going to take that value, you are going to do this first number that we have it divided by that sum. This divided by that sum. So that's exactly what's going on here. In case if you are wondering what's happening, so that's what's happening here. So when you do this, it's going to give you this attention weights that you have here. But in practice, this is not encouraged because there is far more efficient way to do this, which is by using your softmax function. So the softmax function is so robust in a way that it helps us to circumvent the problem of underflow or overflow. So if you take a look at the function of softmax, it's one of the properties or one of the beauty of using softmax is that it helps us to avoid such problem, the problem of underflow or overflow. And it's also very manageable to if we're using softmax instead of the normal taking the sum of all the dot products that you've computed and using that to get the attention weight. If you're using your softmax function, it even makes it more favorable for us to perform training, because when you are performing your model training, you have to compute the gradients, you have to update the weights, and when doing this, the softmax function is so elegant in a way that it enables us to avoid running into the problem of vanishing gradient or excluding gradients. So this is just to show that even if you still end up using your softmax function, that the value is still going to sum up to 1. So there is no cause for alarm. So whether you use the original summation that we've seen in the previous slide, or you use your softmax function to get your attention weight, when you sum all the values that you have here, it's still going to give you 1. But it's advised that you always use your softmax function. In practice, this is what is being used. So you rarely see someone using the summation of the dot product to get the attention weight. That doesn't mean that it's not going to sum up to 1, but if you are building for preparing this data, you have it in mind that you want to use what you are doing, not just for learning purpose, but to also take what this is going to produce to further use it in training your LLM using a specific architecture. You are going to make sure that you are using the softmax function so that you can enjoy it. You can have it can help you to avoid the issue of underflow or overflow. Okay, so now we could see that when you use your attention score, it's still going to enable you to arrive at value that sums up to 1. That's your attention weight. When you add every value that you have with your attention weight, it's still going to give you 1. So brushed up on this now. We are then going to move to how exactly do we then get the context vector, given that we now have our attention weight. So the next step is after you've gotten your attention weight, which is your normalized attention score, you are then going to take this input vector that you have, that your journey starts. So each input token has a vector that is associated with. You are now going to take this input vector and multiply it by the corresponding attention weight. After you've done this now, you are going to take the sum. So when you sum, it's going to give you the context vector for the second token that you have in the sequence. So this code is just briefly showing us how exactly this works. So you are going to take each and every value that you have here. So this is the context, this is the vector for your first input token, for the second one, for the third one. So now you are going to multiply this value that you have here with the attention weight that we've already calculated. So remember that you are going to sum all this. So when you sum it, it's going to give you this. So this guy that you are seeing here is what we could refer to as the context vector, specifically the context vector for the second token, which is Johnny. So based on what I've explained so far, when you look at this picture here, it should start looking customer friendly by now. Remember that we started by breaking down these values that you have here into an input vector, which you are seeing here. So your corresponds to this input vector, and the embedding size here is 3. So the second input vector corresponds to this, the third one corresponds to this. So for you to be able to compute the context vector for the second input token journey, you have to first of all get the attention score. And how do we get the attention score? You use dot product. Once you've gotten the attention score, you have to get the normalized attention score, which is your attention weight. Once you've gotten your attention weight, for you to now get your context vector, you have to take this attention weight that you've gotten, you have to multiply it by this vector. Multiply this attention weight with the second input vector, and multiply this attention weight with the third input vector, etc. Once you've done this, now add all these values together, add the result that it's going to give you. That's what's going to yield this context vector that you have here. So I've summarized what I was trying to explain over the last couple of minutes. So when you look at this picture, you should fairly be able to explain or understand the flow of the whole thing. Okay. So now that we've seen how to compute the attention weight of the attention weight of the values that we have, and how we use this attention weight to get the context vector of a single input token, specifically the second input token that we have. We are now going to look at how then can we compute the attention weight for every input token. Remember that I started by always using Johnny as a query token. So, but what then happens if we want to see the context vector, not just for Johnny, because this context vector you are seeing here is a context vector that corresponds to the second input token. So as you can see, even the attention weight that you have here is trying to tell you that this attention weight that you have here is the similarity between this guy, that is your first input token, and the second guy. So this is also the weight that corresponds to this second input token, Johnny with itself. This is the attention weight that corresponds to this start guy and Johnny. So everything we've been doing so far, we've sort of made Johnny the center of attention here. But what if we want to be able to get the context vector of the first input token. The second one, the third one, for every element that we have in our input sequence, we are going to look at how to do that using the concept that we've learned so far. But now we are not just going to focus on Johnny. We are going to try to compute the attention weight for all the input token, and at the same time use that to get the context vector for all the input tokens that we have. So this picture that you are seeing here generalizes what we are trying to do next. So when you look at this now, you are going to see that this is the attention weight between you and you, the attention weight between you and Johnny, the attention weight between you and Stats. This guy in orange is what we've worked on so far. So because we sort of focused only on the second input token, but what we are trying to do now is that we are not just interested in getting this value that we have here. We are not just interested in getting this. We want to be able to get the attention weight of everybody. So once we've been able to get this, we are then going to be able to compute the context vector that corresponds to each input token that we have in our sequence. And remember that the values that you have here, so for example, if you notice from our previous slides, when you run this yourself, okay, so when you run this, you are going to notice that this is the attention with the first the attention with that we have, the first value that we have there, 0.138. I always try to, I don't exactly use the complete value or the complete number so that we don't have it taking up much space. So this is still pointing to what I just showed us, 0.13. So this time I just made it 2 decimal places so that we can save space. So that's what I'm trying to point out here. And remember, when you add all the values that you have in each row, it must sum up to 1. When you add the values that you have here, it must give you 1. If you add this, it must give you 1. So now let's look at the steps for us to be able to compute the attention weight of all the input tokens that we have in our sequence. So the first thing that we are going to do, of course, is for us to get the attention score. Once you've gotten the attention score, you are going to normalize this attention score to give you the attention weight. Once you've gotten the attention weight, you then have to multiply this attention weight with the corresponding input vector and then sum everything to give you the context vector that is related to the particular input token that you are dealing with at that point in time. So computing the attention scores now. So this value that this code that you are seeing here is simply a code that shows us how we can compute the attention score. So each element that you have in the token represents the attention score between each pair of inputs. So this, what you are seeing here, is representing the attention score between you and you. This is showing you the attention score between you and Johnny. So when you come to the second input vector now, so this is showing you the attention score between you and Johnny. This is showing you the attention score between Johnny and Johnny, like that. So I believe we can understand what's going on here. Now remember that this attention score is still unnormalized at this point. So for us to be able to get this attention score to become attention weight, we have to normalize it. And for us to be able to do that, we have to use a softmax function to do it, such that once we've performed the normalization to get our attention weight, when you add all the values that you have in each row, it's going to sum up to 1. So, but for now, this value that you are seeing here is just the plain attention score, which is yet to be normalized. So if you notice from the last slide, I used for loop to compute the attention score. And it's not exactly a good coding practice when you are using for loop to do such, because for loop takes it takes a whole lot of time. So instead of using for loop, we could simply use this matrix multiplication a symbol to multiply multiply the input with the transpose of itself for us to be able to give us this, for it to be able to give us these attention scores that we have here. So this is way more elegant and very fast compared to the last slide where I'm using for loop. This is going to take much time compared to just use your at symbol to perform this multiplication, vector multiplication. Okay. So now that we've performed the multiplication here, and we've gotten our attention score, the next thing for us to do is to get our attention. So we have to use softmax, which is what I'm using here to get the attention weight. Now, when you sum up the values that you have in each row, it's going to give you 1. So now this is the second step now, which is computing the attention weight. Remember that the first step is you have to first compute the attention score, which is simply by doing dot product. Once you've done that, you move on to the second step, which is where you compute the attention weight, aka you just normalize the attention score that you've already computed for you to get the attention weight using your softmax function. So the third step is for us now to compute the context vector, or the context vector now. So what then happens is that since we've gotten our attention weight here, the next thing for us to do is that we are going to take this attention weight that we've computed and multiply it with the corresponding input vector for each of the tokens that we have in our sequence. So when you perform this matrix multiplication once more, it's going to give you this. So this tensor that you are seeing here is a context vector. So now if you notice, if you go back to our previous slide, that's what we started off with. When we computed the context vector for the second token in our sequence, this was the result that we got. So what this is trying to tell you is that the context vector for the first token is this. Remember that it's still in an embedding. The embedding size is still 3, since that's what we use from the onset. So this is pointing to the context vector of your first token, the context vector of the second token, which is journey. So this is your journey starts with 1 step. So what we have here is a context vector for each of the tokens that we have in our sequence. So now that we've sort of seen a more general overview of how we worked from getting the attention score to the context vector without having a trainable weight. So now we are going to try to look at self-attention that has a trainable weight. So now we are going to introduce trainable weights, which is exactly what gets updated when you are using your transformer architecture to train your LLM. So why I started from the first part is that I want us to first have a very good understanding of what this attention team looks like without any weight. So once it's fairly clear to us now, we can now introduce this weight for us to then see how to move from a simple self-attention without a trainable weight to the attention mechanism that has a trainable weight. So where are we currently? We are looking at the attention mechanism. We've talked about a simplified self-attention mechanism without any trainable weights. This is what we've talked about. So we are now going to focus on the self-attention mechanism, but this time with a trainable weight. So the major difference between the first attention that we've seen and the second attention is the introduction of this weight matrix, which is your QKV. So that's the major thing that differentiates this simplified self-attention with the self-attention mechanism trainable weights. So we are going to see how this weight matrix, the role that it's going to play in this second attention mechanism. Okay, So trainable weight matrix. So this is what enables us to deeply understand and leverage the relationships that we have within our input sequence. So we have the weighted sum for context, we have the dynamic weight matrix, and we also have the learning optimal representation. So this is exactly what this weight matrix thing that we're about to introduce. This is what it contributes to the kind of attention that we are looking at, that we are about to look at now. So we are going to introduce the three weight matrix, that's your QKV, to what we've done so far, to see how these three guys helps the attention mechanism to be a bit more smarter without. So the first segment that we discussed is just a very plain or a very simple attention mechanism without any trainable weights. So if we then want to use this attention in training our LLM, it's important that we introduce this weight matrices. That's your QKV matrix. Okay, so everything still looks like what we've seen before. The only difference now, or the only thing that is changing, is we are introducing this weight matrix that you are seeing here. So we have three weight matrices that we've introduced. So we have our WQ for query, the weight matrix for the key, and the weight matrix for the vector as well, which is going to, for each input vector, we are just going to add that to each and every one of them. So that's the only thing that is changing. So since we started by making Johnny the special candidate, we are still going to continue in that line. So here you could see that this corresponds to this. This is the second input token that we have, and this is the input vector that corresponds to the second token. So when you introduce these three weight matrices, that means that you are going to have a matrix that caters for the query, you're going to have a matrix that caters for the key, you're also going to have a matrix that caters for the value. So this is specifically for the second input token that we have. So how then do we compute our QKV vector? So we are going to first start off by trying to understand this picture, which I've explained before in the last slide. So this weight matrix that you are seeing here, we have the three of them. So the first one corresponds to the query, the second one corresponds to the key, and the third one corresponds to the value. So for us to be able to obtain the value for this weight matrix that we have here, we still have to perform normal matrix multiplication that we introduced before. So you are simply taking the second input token that you have, and you are going to multiply this by your weight matrix, that's WQ. When you multiply this guy with this, it's going to give you this. When you multiply the same guy as well with this, it's going to give you this. When you multiply this with this, it's going to give you this value that you have here. So we are going to do the same thing for, say, if you are focusing on this, the T input token that we have, or if you're focusing on the fourth or the fifth, so the process is still the same. Okay. So now that we've introduced this trainable weight matrix, we are going to start off by making the second input token to focus. We are going to focus on the second guy. Then once we've been able to understand how the flow works, when we are now working with a self-attention mechanism with trainable weight, specifically with being able to help us to compute the context vector for the second input token, we can then extend this now to be able to do the same thing for all the input tokens that we have. So we are going to once again try to understand it with the lens of using the lens of the second input token that we have. Once we've been able to see how we can work from the input token that we have to getting the input vector that corresponds to the second input token, we can then use that to get the QKV matrix and eventually get the context vector that corresponds to the second token. Once this has been established, we can still use the same idea to get the same thing for all the input tokens that we have. So with that being said, so this code that you are seeing here is simply how to go about this. So we started by picking the second input token, which is our bright guy here. It has Johnny. Remember that when you index with 1, it's going to point you back to this guy that you have here, which is the second guy, the second row here. So we also have to specify our input embedding size. So the input embedding size is simply, you have to count how many elements you have inside each of these vectors. It's 3. So the input embedding or the embedding size of the input is 3. Now, the output embedding, I decided to use 2. So you have to, these are the 3 variables that you need to have in place for you to be able to get your 3-weight matrix as your WQ, WK, and WV. So what we are doing here is that we are simply initializing or instantiating these 3-weight matrix. Remember that this is just going to randomly create a weight for us that corresponds to this, that corresponds to the number of input dimension and output dimension that we specified. Okay, now I used false here because this is just for explanatory purpose, but then when you want to perform your real model training, you will do well to remember that you're going to change this from false to true, because when you don't change this from false to true, this is not going to get onto the computational graph. So for people that are familiar with PyTorch, so if you then want to perform your model training and you're updating you want to perform your weight updates, this is not going to be updated. So why I used false here is because I don't want to have a lot of baggages, since this is just for explanation's sake. But if you are doing real, you want to do real training, please remember to use true. So now that we've initialized these 3-weight matrices here, what we are then going to do is that we are going to multiply the bright star. Remember that our S2 is still pointing to Johnny, this guy that we have here. So this is where we created it. So you just have to multiply this vector, that's the second input vector, with the weight matrix for query. You're also going to do the same thing for the weight matrix for key. You're also going to do the same thing for the weight matrix for value. So once you've done this now, you now have, you've successfully computed your query vector, your key vector, and your value vector. So when you now print, for example, when you print your query, this variable that you have here, query 2, it's going to give you this tensor. So, and remember that before we started off this, we specified that we would like our output embedding to be of size 2. So this explains why we only have 2 values here, because specified that we want the output embedding size to be 2. So please don't get confused when you hear weight parameter versus attention weight. There are 2 different things. So your weight parameter is what gets updated. Is when you are performing your model training. This is what changes when you are performing your model training. When you are doing your back propagation, the computing the gradient, and you're updating the weights, this is what is changing. So when you hear of model training, it's simply adjusting this with parameters in such a way that at the end of the day, it's going to enable you to, the values that you have here, it's going to enable you to minimize the loss function that you have. Then for attention weights, this is what helps us to determine to what extent a context vector depends on several other parts of the inputs that we have. So those two things are not, they are not the same. So don't be confused when you hear me say weight parameter versus maybe attention weights. They are entirely two different things. Okay. So this is the same thing that I've discussed before. When you try to get the shape of your key, it's going to give you 6x2. When you try to get the shape of your value vector, it's also going to give you the same thing. And remember that we have, what this is trying to tell you that is that you have 6 rows and two columns there. So the same thing for your value as well. So now you've seen how we've successfully been able to project these are input token from being in three-dimensional space to two-dimensional space. This is because of this guy, because here we specify that we would want the output embedding to be of size 2. So it's no longer 1 by 6 by 2. So or in three-dimensional space, we've been able to project these input tokens now from being in three-dimensional space to being in two-dimensional space. So now that we've successfully gotten this value that you have here, we've seen how to get the KQV vectors. We are now going to see how we can compute our attention score. From our KQV vector, we are able to establish that for us to be able to get these values that you have here, you have to first perform the multiplication. So when you multiply each input vector that you have with the corresponding weight value or the weight matrix, it's going to give you the vector for K, the vector for V, and the vector for your Q as well. So now that we've gotten this, we want to now use this vector to get to compute our attention score. So as usual, we are also going to perform the normalization. So once you've multiplied and you normalize, it's going to give you your attention weight. So let's now see how to, first of all, compute the attention score before we move on to see how we are going to normalize it to get our attention weights. So remember that we started by initializing these three Y's here, our 3 weight matrices as your weight matrix for query, weight matrix for key, and the weight matrix for value. And for us to be able to get the query vector, the key vector, and the value vector, you simply have to multiply your x2, which corresponds to this token called Johnny, with the query matrix that you've established here or that you've initialized here. You do the same thing for the weight for vector. You do the same thing for the weight for key. So if you notice here, instead of using x2, which is the vector in the second row here, I'm using the entire tensor here instead of just using x2. Whether you use x2 or you still use the entire thing, which is the input, it's going to give you the same thing. When you look at the row, so here we are multiplying the inputs. That's all the inputs that we have here, which are the key, the weight matrix for key. We are also multiplying the input with the weight matrix for value. So since what we are interested in is still the second guy, Johnny, I'm still performing indexing here to be able to extract the vector that corresponds to the vector that corresponds to the second token, which is Johnny. So once you've done this now, for you now to get your attention score, you have to perform dot product. So in this case, we are simply multiplying using the dot symbol here to perform dot product between our query and our key. So when you perform this operation, it's going to give you the attention score that points to the second token that you have in your sequence, in your input sequence. And remember that this value, this attention score, is still unnormalized. So for us to be able to get the attention weight, we need to normalize this. So when you normalize it with softmax, it's going to give you a normalized attention score, aka your attention weight. Okay. So this is me pointing out that when you perform this operation, when you perform this operation, that the value that you got here, the value that we got here, which is the second guy, this is pointing to Johnny. It's still the same. It's still the same value that we got when we decided to focus just on when we decide to focus just on the second input token that we have. That is with regards to computing the attention score. That is this guy that you are seeing here. So that means that this is the attention score for the first guy, for the second guy, the third, fourth, fifth, and sixth. So this is the attention score for Johnny, for stats, for width, for one, and for step. So now we want to go from the attention score to the attention weight. And how do we go from this attention score to the attention weight? We simply have to normalize the attention score that we've computed using softmax. So here you could see that when you normalize your attention score, this period, remember that what we did before so the difference between your simplified attention mechanism and when you now have a trainable weight in your attention mechanism is that we are normalizing this our attention score with the square root of our decay. So this decay that you are seeing here still corresponds to the last dimension that you have in your key. So if you remember that you're also going to take the square root. So the reason why we are dividing this by the square root of the embedded dimension is we want to be computed with, we want to perform the scaling such that when you are dealing with a self-attention mechanism with trainable weights now, it's going to enable you to avoid the issue that comes with overflow or underflow. So that's the major difference between when you are dealing with a self-attention mechanism that doesn't have a trainable weight and the one that has a trainable weight. Remember that you are still going to divide your attention score again by the embedding size, the square root of the embedding size of the key. So when you do that, it's going to give you this. Okay, so I think I've explained this as well. So the reason why we have to divide again, why we have to scale, is to avoid the issue with underflow, overflow, your vanishing gradient issue. So for stability, you have to remember to divide by the embedding dimension of the key. And is take the square root of the embedded dimension of your key for this scaling. So now that we've computed our attention weight, the next thing is for us to now compute the context vector. So since we are still very much working with just this in mind, the second input token in mind. For us to be able to get the context vector, that means that we now have to get the attention weight for this, get the attention weight for this, get the attention weight for this, and put everything together to give us this our context vector that we have here. So after you are done with the multiplication, multiplying the attention that you have there with the input vector for each and every one of them, you have to add everything together to get your context vector. So it's similar to what we did in the first attention mechanism that we saw. So that's exactly what's happening here. So for us now to get our context vector, given that you've gotten your attention weight, you have to then multiply it with the weight matrix of value, your weight matrix for the value to get the context vector. So the only thing that is different here is that we are taking this attention weight that we have and we are multiplying it by this vector, by the weight matrix for the value to give us this context vector that corresponds to the second input token that we have in the sequence. Okay, so what exactly, why do we have to have this key, this query key and the value thing in attention mechanism? So the main reason is because introducing this KQV matrix allows the attention mechanism to be able to weigh and combine information from the entire input sequence. So it's just going to know, or direct its focus on what's more relevant to the output or to each of the outputs. So it's what tells your attention mechanism that this is important. This is not so important. This is maybe not that important. So that's the essence of having a Q and a K and a V weight matrix introduced. So now that we've seen a brief overview of your self-attention mechanism in trainable weights, we are going to try to code this now in Python. Okay, I did it somewhere, so I just briefly switch to show us what this looks like. So later on, we are going to get this. We're going to get this Jupyter, this IPython notebook, and possibly Python scripts for people that prefer using for people that prefer to run this using VS Code or using a .py script. You need to install these two guys. This watermark is not really important, but you need to have PyTorch installed on the machine for you to be able to run this. So here we imported our dependencies. You just need the neural network module and Torch itself. So this is what the implementation of your self-attention looks like. You see that it's not really that complex. So once you are able to grasp what this self-attention guy is all about, then it's easier for us to look at the casual attention mechanism or the maxed attention mechanism, and alternatively combining the self-attention mechanism and the casual attention mechanism together to understand the multi-head attention mechanism. So what you are seeing here is what I've been rambling about for some few minutes. So this is just how to code your self-attention mechanism. Now here, I need to point out something. Here, when I created this, my three weight matrix, WQ, WK, and value weight matrix, I use the parameter function here. So for This is not the only way to do it. You can as well use your nn.linear to do this. And it's going to give you the same value. So I also showed that if you don't want to use this, personally, I prefer using nn.linear. So if you want to use nn.linear, you can also do that without having to use a parameter guard. So here we created our class, which inherits from the PyTorch neural network module for us to be able to do a lot of stuff that relates to coding neural nets. And here we initialize, we are calling the super function to invoke the constructor of the parent class. Then here we created our three-way matrix, query, our key, and our value. We simply instantiated these guys. So now for us to be able to get our vector, our key vector, our query vector, and our value vector, we need to multiply. I've explained all this before, but this is just it in code. You need to multiply this, your input, with the key. You need to multiply it for you to get your query vector. You need to multiply this with a query matrix. You need to multiply for you to get the value vector. You need to multiply this with your value matrix. Once you've done this part, the next thing for you to do is to get your attention score. For you to get your attention score, you simply need to do multiply your query with the key transpose. So when you do this, it's going to give you your attention score. Once you've gotten your attention score, the next step that you need to take is for you to get your attention with that. So you need to get the normalized version of your attention score, aka your attention weight. And for us to be able to do that, we need to use softmax function. But don't forget that you need to add this. You need to divide. You need to divide with the square root of the embedding size of your key. So once you've done this, this is going to give you your attention weight. Now, for you to get your attention, your context vector, rather, you have to take this attention weight that we've computed, multiply that with your value. That's the guide that we computed here to get your context vector. So this is me showing how to use this. So we created this tensor called inputs, the same vector, the same image that you've been seeing so far in the slides. So this is the same vector. So the next step is for us to specify the input size of our embedding and the output as well. So this is simply pointing to the number of our embedding size, which is 3. So this is simply the number of columns that you have. You have 1, 2, 3, or alternatively, you can simply count the number of values that you have in a vector, in a single vector. So you have just 3. So this is the input size of the embedding. Now, for us to proceed, you also have to specify the output. So here we are simply using 2. Now you create an object of your self-attention class and pass in the required arguments. So this is going to give you this guy. It's going to return this context vector that you are seeing here. And of course, it's going to be in 2 dimensions. So it's just 2 values that we have here. The first dimension, the second dimension, which is as a result of specifying that we want the output dimension to be 2, or the embedding size, the output embedding size to be 2. Alternatively, if you don't want to use the nn parameter, you can as well use this nn linear. I prefer using this. So this is going to give you the same value, but remember that you need to turn off the bias feature if you want to use your nn linear. So this is still doing the same thing that I showed us that is possible with your nn parameter. So when you do this, it's going to give you this context vector that we've seen here. Okay, so let's move back to our slide, talk about casual attention. We've covered quite a lot. So we are supposed to start. Okay, we've done this. So the picture you are seeing here is just an overview of what your self-attention mechanism does. So the next step is for us to look at the casual or the masked attention mechanism. So if by now I am going to presume that when you look at this picture, it should start making sense now. So because I've explained how the whole thing, the flow of the whole thing, and I've also shown briefly how to put this in code or how to code this. So you always start with your inputs. So if imagine that the number that you have or the number of the embedding size is 3, and you have about 6 words or 6 tokens. So this is what we are going to refer to as our X. So the embedding vector for the second token, that's this guy that you are seeing here. So once you have this, the next thing that you need to do is that you need to create these 3 guys, these 3 wise men. You need to create the weight matrix for Q, A, V. Now, once you've created this, you are going to then try to get the query vector, your key vector, and your value vector. And how do we do this? You are simply going to take this guy, multiply it by your x2, or with this vector that you are seeing here, multiply this with this, it will give you this, multiply this with this, it's going to give you this, multiply this with this guy, it's going to give you this. So now that you have your query, your key, and your value vector, next thing for you to do is you are then going to compute your attention score by simply doing multiplying your query vector with the transpose of your key vector. Once you've done this, it's going to give you your attention score. And for us to get the attention weight, we have to take this value that we've gotten and multiply that with the value vector that we have for us to be able to get once you've gotten your query vector and your key vector, you compute your attention weight matrix. Once you've gotten your attention weight matrix, which is this guy, for you to now get your context vector, you need to take this guy that you're seeing here, this attention weight matrix that you're seeing here, multiply it with this value vector for you to get your context vector. So that's a summary of what's going on in this image. So now that we've discussed this, let's move on to casual attention. Okay, so the next thing we're going to look at is casual attention and multi-head attention. So with casual attention, this casual attention guy is not really, it's nothing too spectacular. So what this casual attention is all about is, we can also refer to it as the max attention, is the kind of attention where we prevent the model from seeing future values or future tokens. We want to restrict the freedom of this model from seeing only the current token and the previous token that it has generated. So which is how your LLM makes prediction. So when most LLM are autoregressive, by the way. So when they make the first prediction, they take everything that they've outputted, take it in again as the input for it to get the next token. So this is what it's going to keep doing until it has finished predicting or generating a text that you've asked it to generate, or whatever it is that you've given it to do. Then for multi-head is simply when you now take this casual attention guy and your self-attention. In fact, multi-head is just when you have multiple stacks of your self-attention. But at the same time, we also have to implement this casual attention or maxed attention in it. So let's look at what exactly this casual attention is all about. So, like I said, this is how your LLM makes prediction. If you were in my first section, you most likely have seen this image before. So, like for example, you want your LLM to perform text completion. This is the input that maybe you go to your chat GPT and you want it to complete a text for you. You key in LLMs. So when you key in LLMs, this is the input that you are giving your chat GPT. So what's going to happen is that this guy will start generating text. So the first thing that it's going to do is that it's going to try to come up with this learn. So in the first round, it's going to come up with learn. Remember that from here to here, we don't want this model to see this. So this is simply the context. So the casual and casual attention is we want to hide, we want to max out this guy that you are seeing here. From here to here, you should not see it. Then when it goes a second time, it's going to now take LLMs and learn as the input now. It's going to predict too. When it's going the third time, or when it's generating the third text, it's going to take LLM learn to, as you're seeing here, as the input. It's going to keep regressing like this until it has fully generated or completed the text. So the idea here is that most LLM are autoregressive, and when you are performing training, we don't want it to see this part. We only want it to see the input and the targets. We don't want it to see the whole thing. So for us to be able to ensure that this model is not actually seeing this, the parts that we don't want it to see, we need to ensure that we max out those future tokens. So what helps us to do that is the casual attention. Okay, so with that being said, this is a pictorial representation of what masking looks like. So what you have here is the attention weight of the input tokens that you have in your sequence. So imagine that you want to implement the casual attention now. You are going to hide some parts. So you are going to mask out some parts. So we are going to mask out the attention weight above the diagonal and then normalize the unmasked attention weight in a way that when you still add up the rows, it's still going to give you, it's still going to add up to 1. So this is 1, 1, 1, 1. It's still going to sum up to 1. So we are masking out, you see this diagonal that we have here. From here upwards, we want to hide them. So that's from here, yeah, like this down, we want to hide all this place. Once we've maxed this out, we have to normalize again so that when you take the sum of each row, it's still going to give you, it's still going to sum up to 1. So to apply casual attention, this is the flow. So one way to obtain your maxed attention weight is to apply your casual attention. Then after you've done that, you renormalize again. You use your softmax function to normalize the attention score. You are going to do this in such a way that once you've performed the normalization and you then take the sum of each row of the resulting new attention weight, still going to sum up to 1. You will understand better when you see. So let's look at the first step. So the first step in computing, or the first step here is that we need to compute the attention weight using our softmax function. Yeah, so like I mentioned here, for convenience, I'm reusing the query and the key weight matrix from the code I showed us, the self-attention version 2. So I'm reusing the queue and the query and the key weight matrix step. So which is what I'm doing here. So doing this is going to give you the query vector. Doing this is going to give you the key vector. And for you now to get your attention score, remember that you're going to multiply your query by the transpose of your key to get your attention scores. Once you've gotten your attention scores, the next thing that you need to do is that you need to normalize with softmax. Don't forget that you need this. You need to divide by the square root of the embedding of your key. Then Once you've done this, it's going to give you your attention weight. And when you print that, it's going to give you something like this. So this is the first step. I want to believe that everyone here understands what's going on here. So once you've completed this, your softmax, once you've completed your attention with using your softmax function, the second step now is where you now create that max. You want to hide some parts. So here we are using PyTorch's triangle lower to perform the masking. So to understand what's happening here, we are going to explain this up. We've explained from here to here. So this part is what's new. So for you to get the context length now, you are going to take the how many tokens do we have in this input sequence. So when you do this, it's going to give you your context length. Now, this is where we are simply creating the mask. So the first thing that we're going to do is we want to create a mask that is going to enable us to hide some parts of the future tokens that we don't want it to see. So usually, for us to be able to achieve this, we use a triangular lower function from PyTorch. So we started by creating a square matrix of size 6 by 6. Remember that your context length is what? Is 6. So you are going to create a square matrix as a matrix of ones. So this is 1, 2, 3, 4, 5, 6. You have 6 rows. 1, 2, 3, 4, 5, 6. You have 6 columns. So it's a square matrix of 6 by 6. So once you've done this now, you are going to try to use this triangular lower to create the mask that you have here. So by default, it's going to start creating the mask. Remember that this is the diagonal. I want to believe everyone is seeing Microsoft. This is diagonal. This is the diagonal from here down to this place. So when you are by default, when you are creating the mask, it always shifts it up by 1. So by shifting it up by 1, not ordinarily, if you want to place 0 in the diagonal of this tensor that you have here, you're supposed to start here 0, 0, 0, 0, 0, 0. But by default, it's going to move it up 1 by 1. So meaning that it's going to start masking from here. As this is going to be from here down. From here down upwards, it's going to be filled with zeros. So that's what this guy is helping us with. It's helping us to do. Okay, so once we've done this now, the next thing is for us to multiply these marks that we've created with our attention weights. And we know that whatever 0 encounters in multiplication is going to render that part to be 0. So when you multiply this new mask, this guy that you are seeing here, this guy, when you multiply this guy with the attention weights that you've computed, the attention weight you computed here, once this 0 meets, so this part is going to disappear. So it's going to be marked with 0. So, well, as you can see, what we have here currently is still the unnormalized version. So this is just your attention score. For you to be able to get the attention weight, you have to normalize so that when you sum the values that you have in each row, it's going to sum up to 1. But this doesn't look like it's doing that yet. So we still need to perform a normalization. So renormalizing now, we are going to, so this is me still using the row sum, but a far more efficient way of doing this. So when you use the row sum, this is just for us to understand what's going on. So when you use the row sum, it's going to normalize this your attention score to give you the attention weights. Now, if you compute the sum of each row, it's going to give you 1. It's going to give you 1. So, but there is a more efficient way of doing this instead of what we just looked at now. So if you are optimizing for efficiency and speed, this is a more appropriate way of doing it, or a more practical way of doing it. So the reason why I did this is for us to have a picture of what exactly this masking thing looks like and how it's achieved. So a more practical way of doing this is what we're about to look at. Instead of filling with zeros, or instead of masking with zeros, we are going to use negative infinity to perform the masking. And there is a reason for this. So mathematically, we are, so the casual masking now before we get to the math part. Instead of doing zero masking, it's encouraged or more in a more practical sense that we mark with negative infinity. So this still points to softmax. So if you look at the formula of softmax, you are going to notice that when you have an exponent to the power of a negative infinity, this is going to tend to zero. But when you have an exponent to the power of zero, this is going to tend to one. So this is going to introduce information leakage. Imagine the when you want to you've gotten your attention scores now and you want to perform normalization using softmax for you to be able to get the attention weight. If you use this softmax formula, so when this softmax formula encounters areas where you have zero, instead of that place to still remain maxed, it's going to make that place to be one, and that's not what we are gunning for. We want to make that place to still be blank, to still be vacant or masked. So for us to be able to achieve that, we are going to ensure that we fill or we mask with a negative infinity instead of zero. So what I'm trying to say is, you see this area that we marked with 0, 0, 0, 0. We need to, if we want to perform the masking, we need to mask it with negative infinity, negative infinity. And I've just explained why. It's much more efficient. And if we are putting the mathematics of softmax into play here, you are going to notice that if you raise anything to the power of zero, we know, I want to believe that most of us know. So when you raise anything to the power of zero, it's going to give you one. So this, which is still leaking info. Remember that the part that we masked or we intended to remain hidden is the future token. We don't want the model to see that part. But now, when you now run this, when you now run your softmax during normalization, if you pass your softmax to this tensor that is somewhat filled and somewhat maxed, once your softmax encounters those places that you have zero, that place is not going to remain maxed. It's going to now give it a value of one, which is what we are trying to avoid. So that's the reason why that's the more reason why we mask it negative infinity. Okay, so let's now see how that works. So we are going to replace the zero masking with excuse me, masking with a negative infinity. And this is the part that helped us with that. So starting from here, we created a mask. So this then becomes triangle upper. Once again, we are going to create a squared matrix of 6 by 6. So this time, it's going to be a matrix that contains only ones in it. Now, the diagonal is 1 here. So what that means is that it's going to start the masking by moving a step, one step. So instead of the masking to start from here downwards, it's going to move one step. Then it's going to start from here and perform the front. So that means that from here upward now, it's going to be filled with negative infinity. And why this part was filled with negative infinity is due to what we have here. Remember that we first created a tensor, or we first created this squared matrix that contains only ones in it. And we use this triangular upper to perform the mask thing. Now, what's going to happen is when you now call this masked field on these attention scores now, you see those places where you have, remember that we are using triangular up this time. So it means that from here, this place is going to be, I wish there's a way I could illustrate or draw something, but this part is going to be 1, 1, 1, 1, 1. Everywhere it's going to, these places that you are seeing infinity, it's going to be 1, 1, 1, 1, 1. Since we are creating a mask. using these touch dots ones. So here is going to be 1, 1, 1, and every other place. So here, 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 here. Every other place that you are not seeing negative infinity is going to be filled with 0. That's what this mask will give you. Maybe when you run through this code yourself, or when you are experimenting, try to print mask so that you see what's going to give you. So every other place that you're not seeing negative infinity will be masked with 0. Now, based on what we did here, we are now calling this method on this attention scores tensor. So what's going to happen is that we have this bool value. So imagine that you are taking this, let's for a moment imagine that this tensor that we are seeing here is filled with zeros and one. Now the places that you are going to have one is where you have your negative infinity, which is here, here, here. All the places that you have negative infinity is going to be filled with 1. And every other place that you are not seeing negative infinity is going to be filled with 0. Now, what this masked field is going to do is that it's going to use this marks that we've created now. Any place that it sees 1, remember that in Boolean terms, your 1 corresponds to true and your 0 corresponds to false. So any place that is seeing 1, it's going to just fill that part or mark that part with negative infinity. So since this place are the areas where we have 1, 1, 1, 1, so this place is going to automatically turn to negative infinity. Now, any place that is unable to encounter 1, so all these areas now is going to fill it with the original value that we had in this attention score matrix. So that's why this part you are seeing values there, and this part is just marked with negative infinity. If what I said now is not customer friendly, is not looking like it's clear, you understand better when you pick this piece of code and just once you've created this mask, print it. Once you've created masked, print it as well, so that you see what exactly is happening here. But what I explained is just a summarization of what goes on when you run this code. So now that we've gotten our marked, we've been able to mark some parts, we are now going to apply a softmax function to get our attention weights. So once you've applied your softmax, it's going to give you this. Now, when you take the sum of each row, it's going to sum up to 1. So the next thing now is that we are now going to take this our attention weight now, use it to compute context vector. So before we move on to adding context vector, there is an additional thing we need to also look at. So we are also going to add dropout. So you probably might have heard of dropout if you've done anything with deep learning before. So dropout is simply the technique where we randomly select a hidden unit layer that is going to be ignored during training. So you're just going to drop them. And the reason we do this is for us to prevent overfitting. So if you want your model not to overfit, you usually would add dropout layer to your network so that it will just randomly drop out or ignore some hidden layers during training. Remember that this dropout is only applied when you are training. You don't add a dropout when you are trying to perform inference, or it's just what we use to prevent overfitting when we are training around it. Okay, so there are two places we can apply this dropout thing. So we can decide to apply or add the dropout guy after we've calculated our attention weights, or we can add it after we've calculated our context vector. So I chose to do that after we've calculated our attention weights. So that means that you can either do it after you've calculated add your dropout layer after calculating the attention weights, or after computing the context vector. So what exactly does dropout introduce now? So this dropout introduces an additional masking, if we can use that. So This is the original attention weight that we've marked. So, but now when you apply your dropout, it's just going to randomly add an additional mask. So this is the dropout mask. So it's just going to randomly mask out some at random, mask out different positions. So at the end of the day, when you have this your marked attention weight and you are adding an additional masking, which this dropout guy is going to introduce, we are going to end up with this dropped mask. Remember that we do this to prevent overfitting. So we are going to use a very simple example to understand how this works. So I added this very little code here. So we are going to use a dropout rate of 50%, that's 0.5, which means that half of the attention weights that we have, it's going to be ignored or dropped. And for us to understand or contextualize, I created this tensor of a 6x6. Remember that the dropout rate we are using is 0.50%. So when you call this dropout from your example, you could see that it's just going to randomly drop out some positions in your tensor. So the places that you are seeing 0, the places that you are seeing 0, 0, 0, 0, 0, 0, those are the places that it has marked or it has dropped. Okay. So if you want to calculate, oh, what happened? I thought that we created a tensor that has just ones in it. How come we're now seeing 2 here? How did this 2 come about? So what happens is that this dropout applies the formula. So it has to recalibrate. So it's going to rescale, if I could use rescaling. So when you apply dropout, aside that it's going to randomly drop some positions in your tensor on your attention weight matrix, it's going to rescale again. So it's going to rescale the remaining part that is not dropped, and this is the formula that it's using. So, for example, it's going to calculate 1/1 minus your dropout rate. So remember that your dropout rate that we used is 0.5. So if you do 1 minus 0.5, it's going to give you 1/0.5. So when you do 1/0.5, it's going to give you 2. So you are going to get 2 for your 50% dropout. So that explains the reason why we have 2 here. It's because it's rescaling. So this is what the dropout is going to give you. You can try this with, if you change this value here to say maybe you want the dropout rate to be 20%, that's 0.2. It's going to use that same formula, to rescale. So you can try it out. You can play around with this when you are experimenting with the code that you have here. I just have 2 minutes to round up them. Okay, so when you apply dropout after you've added your masking, dropout of 50%, so you are going to have something like this. So the code to this is also here. I don't know if I'm going to be chanced to cover the multi-head since I barely have any time left. So this is the code for the attention, the casual attention or the maxed attention. So I want to believe that this is self-explained, given that you understood the first part, which is the self-attention. So what we are doing here is not so different from what we did in the self-attention. However, the only thing I introduced is I introduced dropout guy, which I've explained. Then I also introduced this attribute you are seeing here, this register buffer thing, and I explained what it's doing. But it's not always compulsory for you to have it, but it's something that is quite important for if you're optimizing for efficiency, or if you would want to avoid moving around, moving your tensor from your CPU to that when you start actual model training now. So I believe I also give an explanation on what this register buffer thing is doing for us. Then you have your forward method, and at the end of the day, you have your context vector. It's already time. Okay, so I explained what this buffer thing guy is doing here. So don't worry, you are going to get access to this. I'm going to push this to the GitHub repo so everyone could have access to it and play around with it. So I'm afraid I don't think we'll be able to do much as regards multi-head, but it's already time for us to round up. But yeah, the last segment is where we then talked about multi-head attention. So the code for the multi-head attention is also in the Jupyter notebook I'm going to send to the repo. I'm going to push the repo. So with the code and this slide, I want to believe that you most likely won't have any issue in understanding this last segment. Yeah. So I want to keep to time to not keep everyone. I don't want to go beyond time. So I guess I'm probably going to stop here. But yeah, so this is just the last segment where we are. So with multi-head attention, instead of you now have multiple weight matrices now. So you don't just have a single QKV weight matrix. You have multiple depending on the number of heads that you want your multi-head attention to have. So in this example, I just used two heads. So that's why you have weight matrix Q1, weight matrix Q2. I like that. So and the code for multi-head attention is also in these resources that I'm about to push to the AISOC repo. So once you can lay your hand on this slide and the code I'm going to push to the repo, I believe it should be fine. Yeah. So let's just stop here and thank you for coming to my section once more. So I'm going to switch back to what's the time now? I'm going to switch back to Google Meet. So do we have any questions? Stop presenting again.